So, good morning. Welcome all to this lecture about advanced digital design. I hope everything is working properly. Just remember, if you have any question, just try to put it in the chat at any point. But please do not turn on your microphone. It seems that if you do that, then the sound is really very bad. As usual, I would like to start with some questions. So first of all, do you have any question regarding our previous lecture? Everything clear? Is there someone with some questions? So from my point of view, I believe the two fundamental points that we discussed was, first of all, the concept of advanced digital design. I believe if you have this slide in your head, the one that we have here, then you can just very easily try to, try to put in your head all the information that we are going to discuss. So let's see, our goal is to develop these kind of systems. Yeah, we want to develop a multi-core system. We have more than one processing element, in this example 4, which are working in parallel. All these processing elements inside, they may have some parallelism, maybe with a lot of arithmetic logic units which are working in parallel, or with a single instruction, multiple data. So we are going to move from the standard processing element that you know from your bachelor, the standard RISC processor, to a processor where we have more than one, let's say, unit working at the same time. Finally, if we want to create this system, we will be able to connect the different processing elements with a unified memory. Yeah, but at the same time, we plan to create a communication between the different elements using an interprocessor network. So fundamentally, this is going to be the scheme of our lecture. First, we start the processing element, and then we expand it. Then we go to the memory, standard caches, and then we expand it to have more than one processor at the same time. Then we go to the interprocessor communication. We start with the fundamental interconnect, the bus, and then we expand it with multi-cores. Okay? So some or less, this image is the agenda of our lecture. 100% clear? Good. Then the other fundamental point that we just, I think there is one student with some question.
Could you explain what is not clear for you? Hafijur? So what I wanted to say is that the scheme of our lecture fundamentally is to move from a single processor, like a RISC processor, to a multi-core processor, where inside the processor, we have also parallelism. We are going to cover the processor architecture, we are going to cover the memory, and we are going to cover the interconnects. Fundamentally, this is the agenda of our lecture. Good. So you see, parallelism is the key word that we are going to discuss. Moreover, if you want to understand parallelism, the other fundamental slide that we were discussing was actually this one. So it seems that if you have parallelism, if you have more than one processor working at the same time, if you have more than one unit working at the same time, then you can reduce the amount of time that you need to complete your program. Can someone tell me why very often you are not as fast as you expect? So if you have 4 cores at the same time, why don't you finish normally in 1/4 of the time? Which are the issues that we get here? So that actually this is the Amdahl's law, but which are the points of this Amdahl's law? One is synchronization overhead, good. What else? Load imbalance, synchronization cost, lack of parallelization in part of the software, so the serial part. Yeah, all these scenarios are typically forcing us to have one amount of parallelism which is limited. After some point, it's actually not worthy to have more parallelism. Here you see one example. In a lot of scenarios, when you try to increase the parallelism, you move in this direction, then there is one point after here where actually these overheads are much higher than what you gain. And this is the maximum parallelism that is typically good for your application. Okay? Clear? Then let's move to the next slide that I believe is summarizing our lecture, or what we did in the other lecture, and this is just that. Sorry, not that one. This one. Okay. So if you remember, the idea of this taxonomy was somehow to try to classify all the ways that we can try to, in all the different ways that we can try to do parallelism. And the basic idea is to separate between instructions and data, and then to see that there are 4 particular cases. So when you are talking about a normal RISC processor, the normal one that you have probably studied in your bachelor, which kind of machine do you think it is in this classification? Yes, just a single instruction, single data. Now, what do you think that is the core that you have in your smartphone? Yeah. In principle, since you have more than one core working in parallel, probably it will be a multiple instruction, multiple data. Actually, if you are more precise, you will see that inside the core, yeah, you also have some accelerator, which is internally a single instruction multiple data architecture. Okay, so the right answer is actually multiple instruction multiple data. This will be the best answer, but inside you have single instruction multiple data as well. Second part of the question, so if you check your smartphone, what do you think that you have? A shared memory architecture or a distributed architecture? Which is the view of the memory that all the cores have? In fact, as some of the students point, is a shared architecture. If you have a small amount of cores, let's say 8, 16, something like that, typically it's a good idea to make all the cores available of the memory that you have, the complete memory. We will have to work very hard in terms of the cache to make this easy. Yeah, but if you do that, for the programmer, it's going to be very, very easy. Yeah, all the cores can access the complete memory. This is what typically you have inside your smartphone. But if now we try to 1020 cores, then this architecture is not scaling well, and probably we are going to use message passing. So we will see that there are some multiple instruction, multiple data architectures where we have what we call a shared architecture. Yeah. While there are other architectures where we have more cores where we use a message passing. Okay. Clear? Then my goal for today is actually to give you a couple of examples of these architectures of what is single instruction multiple data in a very short way, and then we will move to a review of the single instruction single data architecture. Yeah, for some of you which have already done digital architectures, it will be just a review. Maybe for some of you who didn't have any architecture in the bachelor about single processor, it will be just new stuff. So here you have, from the conceptual point of view, a very small program. Imagine that we have a vector of 400 numbers. Actually, we have two vectors, source 0 and source 1, and then we just want to calculate the sum. Yeah. In a conventional processor, you will be doing something like that. You have a for loop, and in every step of the loop, you just do one addition. Yeah. How many iterations do you have to do? 400, just that. What will be the difference if we have a single instruction multiple data architecture? In that case, we can assume that we have one architecture where we can do, for example, 4 additions at the same time. And then, with only 100 iterations, we do our additions. Note that now we are doing a vector sum. We are adding 4 elements at the same time. Okay? If you are working with CUDA or something similar, then this will be the kind of program that you could write. You could say, I want to have 100 elements. Yeah. I want to have something like a stream of 4 elements. I want to do the sum. And then here, you will just tell the accelerator to do all the additions, and then it will work in parallel. If you are working at this level, we will see that you have something which is almost multiple instruction, multiple data. CUDA is not just multiple instruction, multiple data, but somehow when you program, this is what you believe. Okay. Maybe we can go into more detail about these structures. First, single instruction, single data. In here, we have a single CPU. So this is what we call uniprocessor. If our processor had one accelerator, we don't care about that. So it's not accounted in this parallelism. Yeah. We are assuming that every time our processor is fetching one instruction and then executing this instruction maybe with a pipeline. For example, we have this program here. We are just loading one instruction, loading B, then doing the addition, then storing the result, doing one multiplication, storing the result, and so on and so forth. Yeah. You see, this is a very, very simple way of understanding instruction in a sequential way. This is what we have seen already in, let's say, a RISC processor. Please note that if you are using pipeline, internally you have something like 5 stages working in parallel. But from the conceptual point of view, what you are doing is that every time you are executing one instruction. Yeah, these, then the other one, then the other one, and so on. And because of that, we don't consider this as a parallelism. Let's move to single instruction, multiple data. The idea is that we have only one stream of information for the instructions. Only one instruction. But when we read this instruction, all the elements P1, P2, Pn, all the processing elements are executing exactly the same instruction. We are working in different streams of data. Yeah, but all these small processors, all these arithmetic logic units, all of them are doing exactly the same. So the advantage is that we have to load only one instruction, so we have to read one from the memory, but this instruction is broadcasted to all the elements. In order to be a bit more flexible, it's very, very common that we can just, for some part of the time, just to remove some of these processors, to even them, so that we have one kind of if. In this particular case, I'm going to do additions, but only the part 1 and 3 will work. The number 2 for this instruction will not do anything. Okay. Typically, this possibility of turning some processors off can be done with the help of some test instruction. Good. So summary, all the active processors execute the same instruction synchronously. Yeah. Only one memory access for all active processors. Yeah. In such a way that we can very easily work with array instructions. Good. Could you tell me one application, one kind of application where this single instruction is working well? In which kind of programs do you think that this single instruction is working well? DSP, yes. A bit more concrete. Cases where you have a lot of arithmetic operations, but actually with a lot of parallelism inside. Applications like image processing. Applications like voice processing, acoustic processing, data processing. All of these architectures, all of these applications, they have a lot of parallelism, and because of that, they fit very well in single instruction, multiple data. Yeah. If you check here the architecture, you will see that we started to work with this paradigm already in the 60s with the Solomon architecture, and then slowly they were increasing and increasing and increasing. Yeah. Around the 90s, we stopped somehow the development of big machines working with single instruction multiple data, and today you see that this single instruction multiple data is mainly in the coprocessors that you have almost in any processor today. If you check your smartphone, you will see that this is a coprocessor which is working as a single instruction multiple data. I have some slides about the summary of single instruction multiple data architectures, so how they evolve. I believe we can skip this for the moment. It's not bringing too much. Yeah, and anyway, we are going to review it later on. The next big kind of architectures that we want to discuss is the multiple instruction, multiple data. What was that? So you remember here the taxonomy. So the idea is that we have different processors here, processor 1, processor 2, processor N, and every processor is working with different instructions. Can be done fundamentally two ways, as we mentioned last week: message passing or shared memory. I repeat it again. In the idea of message passing, one processor can communicate with another one just sending some information, something like an email. While when we are working with shared memory, all the processors see the complete memory. And then if one processor writes in one position of memory, all the other processors can see exactly this change. Yeah. Today, memory structure, MIMD, is one of the paradigms which is more commonly used almost in industry, smartphones, and so on and so forth, but also in high performance processors. Okay. So if we have a look to MIMD, we will see that we have a major concern with the power cost. Yeah. Why? Because we have a lot of housekeeping activities. We have to load instruction. We have to check that all the guys are working in a synchronous way. We have to realize that maybe one processor is writing in the memory and this information has to be broadcast to all of them. We have some synchronization activities and so on and so forth. Yeah. Because of that, yeah, it's efficient, but we have to be very, very careful. Also, from the software point of view, when you write a program for a MIMD machine, it is very, very common, yeah, that you write only one C program, but inside this C program, you describe what every one of the cores have to do. Yeah, we will see that this approach is very common. It's called single program MD. Yeah, since every processor is at a different point in your big program, yeah, somehow they are working asynchronous. Clear? No question for the moment. Good. Now let's focus in the memory. When you go to the memory part, then you see that fundamentally we have these two ways of organized memory. We can have a big shared memory, somehow graphically, you could say something like that. Yeah. Here we have different cores, and all of them can read from the same big memory. Yeah. The advantage is that if some guy is updating one position of memory, then all of the other CPUs, they can see this change immediately. Yeah. The alternative is to say no. Every processor has his own memory. And if this CPU wants to send some values to another one, then they have to send it through a network interface. But this CPU cannot see directly what is going here. It has to be done always through the network interface. Yeah? Clear? So, 100% clear? Again, this is one of the easiest slides that I believe summarize a lot. Clear these two pictures? Good. So if we want to be very precise, what we have here is how this idea of the memory works from the logical point of view. All the processors sees a global memory, all the processors see small memories. But actually, we can also distribute memory physically in a big block or in small pieces. Yeah, we can have a huge uniform memory access architecture, yeah, what we call symmetric multiprocessor, where fundamentally all the cores see all the positions of memory in the same way. So if you try to read from any position of the memory, more or less, it will take you the same amount of time. Yeah, this is a very, very common architecture today. But actually, you can also have the so-called non-uniform memory access. So you can distribute the memories in such a way that some of the memories are closer to one particular processor. So when this processor reads from that memory, it's very fast, but when it has to read from another memory which is far away, then it takes a lot of time. Okay? If we have this, then we have to be very careful if we have different copies of the memory and so on and so forth. This is one of the points that we are going to discuss with more detail in the lecture. Yeah? Good? Actually, non-uniform memory architecture and uniform memory architecture, they are modern applications. They are ways to organize the processors. So if you have an application where you have a small amount of cores, like you have in your smartphone, probably it's a good idea to have something like shared memory and organize the memory as a uniform memory architecture. Yeah, but if you have an application like high performance computing, where you have maybe millions of processors, probably in that case, you are going to use message passing. And since the system is too big, probably you are going to use a non-uniform memory architecture. Okay? Let's say if you want to create a cluster of processors just to calculate the evolution or how to find a vaccine for the coronavirus. Yeah? In this huge cluster of systems, probably NUMA will be a better idea. In fact, today, what we will find most of the time is an architecture where we have small clusters, where inside the cluster, we are using shared memory with uniform memory architectures, but then the clusters are connected with a message passing approach and using, because of that, a NUMA architecture. Yeah. So most of the systems, actually, they are a combination of the two approaches. So if we think in terms of message passing, yeah, you see that the idea is that all the processors are connected by a network. If they want to communicate, they communicate something like sending an email, yeah, sending a message. Each processor has its own local memory, yeah, and fundamentally, he can only work with his own local memory. If he needs some data from another processor, then they have to communicate that data through the bus. Yeah, really, for me, the simile is an email. They are sending emails not through Ethernet, but just through the network on chip that we have. Yeah, a typical architecture for doing this, a typical, let's say, programming model for doing that is MPI, that we are going to discuss in the lecture in the next weeks. This message passing architecture has some advantages and some disadvantages. So which are the disadvantages? First, for the programmers, since we have to make explicit every time when we want to communicate data, the programmer has to write some function just to do this communication. And this is very hard. Yeah, this low-level programming approach is hard in the sense that it's very easy to make an error. Yeah, the data is not shared but copied. So if you have some vector and there are two processors that have to read this vector, then you are going to have at the very end two copies of this huge vector, which is somehow a waste of space. Yeah, and also it's very hard to make sure that if you have one more copy, that all the copies are consistent. Yeah, in this sense, message passing has some difficulties. Yeah. On the other side, you can see it has some advantages. Since the data is in my own memory, then I don't have problems with simultaneous accesses. Yeah. Different processors, different processing units can work on that at the same time, and I don't care. Yeah. Easy to upgrade the communication backbone and then automatically to improve the performance without having to change anything. Yeah. Because of this advantage and disadvantage of message passing, advantage and disadvantage of shared memory architecture, today what you will see is that most of the architectures use something like a mixture of the two. Okay. When we discuss with a bit more detail the architectures, we have to make a small differentiation. So if you just learn something about message passing and so on and so forth, this theory, these ideas were actually developed for multiprocessor systems. When you have different big processors and they are connected with something like internet or something that you put in your PCB board. Today, what we try to do is to put all these processors in the same die. So when you check your smartphone and you see which is zip there, actually your processor, it has a lot of cores inside one die. Yeah, because of that, the theory of multiprocessor system is not one-to-one to what actually we have to do, create a multiprocessor system on chip, which is the goal of our lecture. Yeah. You will see that the fundamental ideas of shared memory and message passing are the same, but in multiprocessor system on chip, we have some differentiation, like for example, that MPSOCs are very resource constrained. We have to be very careful with the amount of memory that we need. We have to be very careful with the amount of register that we need. Yeah. On the one side, we have a lot of interprocessor communication. And because of that, you could say message passing should be a good option. But also, the cost of having wires in a chip is much smaller than to having wires connecting processors. And then in that sense, shared memory architecture should be better. Yeah. The final point is that today, if you want to create a very complex system, you will have to share memory with message passing. Good. Clear that idea? So again, today we need both approaches. Good. And actually, because of that, let's say we will have to discuss parallelism and the two ways of connecting elements in our lecture. The other fundamental point is that if you think today about most of the architectures that we have, you will see that actually there is a trend to have heterogeneous architectures. So somehow there are some, let's say, companies that try to work with homogeneous cores, but like for example IBM and so on, but you will see that most of the architectures are actually heterogeneous. Good. So if I ask you, in your, just as a trivial example, in your smartphone, or better in your PC, do you have an homogeneous or heterogeneous architecture? Let's say you have a quad core in your PC machine. And why heterogeneous? What is the heterogeneity? I mean, you have 4 cores which are homogeneous. But actually, as you said, the architecture is heterogeneous. So what is heterogeneous in your PC? Actually, in the core itself. Exactly, GPUs. So if you check today, you have CPUs and GPUs. They are completely different. Yeah, inside the cores, they are the similar cores. So somehow it is homogeneous. But today, if you want to have acceleration of graphics, you have to do that with a GPU that has an architecture which is especially thought for that task. Almost all the architectures today, they have some part which is homogeneous, but they need some part which is heterogeneous. Yeah. Now for the smartphone, if you check your smartphone, you have a couple of cores. You don't have a GPU. Do you have some kind of heterogeneity there? Where do you have heterogeneous? Well, GPUs, I don't think you have in your smartphone, maybe. Not in mine. You have some accelerators, that's true. But actually the point is that in your hand, you will have a lot of different accelerators and coprocessors. You have some accelerators dedicated to the coding of signals. You will have some single instruction multiple data architecture for decoding images and for working with sound and so on and so forth. Yeah, your cores inside, they will have some heterogeneity. Good. I hope somehow with this, you already get one idea about which are the goals of our lecture and how this single instruction, multiple data, multiple instruction, multiple data fit. Good. Questions until now? So are there some questions regarding this introductory material? Perfect. So now then let's move to the actual contents of the lecture today. What I would like to present today is just a short review of the processor. Before we start, maybe it's a good idea if we just make a very short break of 2 minutes, then we do one half of the processor review and then the second half, so that we are really fresh. Is it okay for you? Then let's make something like 3 minutes, just 3 minutes break, and then we continue with the processor review. Second part of the lecture. Everyone here? So as said, our goal in this second part is just to try to make a review about the processor architectures. For some of you, it's just a repetition. For some of you, something can be new. Nevertheless, probably it's a good idea just to refresh it to the same background. So first of all, which are the general architectures that we have? So in principle, you could say that a typical computer, the fundamental idea of a computer is just to have stored in memory a set of instructions and sequentially to try to execute those instructions. This idea that appears to be extremely simple is actually the fundamental idea of the von Neumann architectures, which are also control flow architectures. Almost anything in software is working with this fundamental idea. Yeah. Actually, there are some alternatives. We are going to discuss it later on in the lecture, but it is also possible to construct one machine where you have something like data. The data knows what do you have to do with that data, and then automatically you just process the data without having a sequential set of instructions. These are the so-called data flow architectures. Nevertheless, normally when you talk about a processor, you just think in the classical control flow architectures, also called von Neumann. Once we take this paradigm, you will see that there are two typical organizations. One is the, again, von Neumann architecture, where we have one memory where we save the program and the data, and the other is the hardware architecture, where we have just two separate memories. Just a very, very small detail. Yeah. Please note that this term von Neumann can be used with two meanings: the control flow architecture, but also the opposite to the hardware architecture. Fundamentally, when you want to create one architecture, when you want to talk with your colleagues from the informatics, you have to separate, you have to establish one interface. And this is what we call, here, the internal and external architecture. The external architecture is actually the instruction set architecture. This is actually what the software guide sees. So which are the instructions that you have, which is the memory architecture that you have, and things like that. Yeah, this interface. From the hardware point of view, we have what we call the internal architecture. This is just how you have organized your hardware, the data processing, the control units, the memory. Do you have one block? Do you have n blocks? And so on and so forth. Yeah. Somehow this is our business. This is the interface with our colleagues with the software. If you think in terms of the ECA, what we have there is fundamentally which are the instructions that we need, which is the memory, which are the elements which are addressable. Are you working or with words? Yeah. Also the alignment in the memory. All this stuff needs to be known. Also, if you want to use this processor architecture, you have to know the interrupt system. So how many interrupts do you have? When you get an interrupt, do you have a change in the registers or not? All this stuff. If you know this, not just the instructions, but also the model of the memory interrupt, or the interrupt, then fundamentally you can start to use that processor. Okay? Then how many alternatives are for organizing this instruction set architecture? Actually a lot. Yeah, you will see that we can classify that depending on the location of the operands, and then we have the register, memory, and star architectures. We will see that there are some architecture where you have instruction with 2 operands, with 3. We have different kinds of operands, and so on and so forth. Different here. Good. Clear what is an ISA? Note that I have put a red point in some of the slides. I believe these slides are, let's say, the fundamental ones that you have to make sure that you remember from your bachelor. So we have said that the memory element is one of the first points. So what is about the memory? Well, which is the size of the memory? Which is the minimum element that we can address from the memory? Can we read bits or we have to read bytes? We have to read words or long words, all that. There is some small detail about this endianness. So when you have a word with more than 1 byte, do you want to put first the most significant byte or first the less significant byte? Yeah. Also alignment. If you have, for example, words, in a lot of architectures, you have to put that in multiples of 4. In others, you don't have this restriction. So all these things are elements that we have to consider when we create our memory model. Yeah. From the hardware point of view, probably the most important part about the memory model is the memory hierarchy. If you check today, almost any architecture, you will see that you will have a hierarchy model. So you will have, for example, some things that you can save into the registers. You have very few of those, maybe 32, but they are very fast. Then maybe you have a cache where you can save more data, but they are slower than the registers. And finally, you have a big memory, very slow. So somehow, when you are moving in this direction, you can save more data. You will see that this inclusion of the cache is one of the most important problems when we want to have a multi-core system. Yeah. If you have this scheme, we have to define how many caches do we want to implement, how many registers do we want to have here, and it's unclear which is the best solution for your architecture. In particular, if you have too few registers, then you will have very often to go to the cache and the memory, and because of that, your system is going to be slow and very power hungry. But on the other hand, if you have too many registers, yeah, then this register file is going to be slower, and also the overhead when you have an interrupt, it's going to be larger. Yeah, you will see that different architectures have different ideas about a good number of elements there. Yeah. When we consider the register file, you will see that there are fundamentally two ways of organizing that. There are some architectures where all the registers are almost the same. Yeah, there are other architectures where every register has a very different meaning. For example, here we have one register which is for input and output. The other is the base register. The other is an index. There is another which is segmentation registers. There is another which is the FER, PC, and so on and so forth. The alternative is these architectures where almost all the registers, not all of them, but almost all of them are exactly the same. Yeah. So if you check an Intel machine, which architecture do you have? This or that? What do you think that you have in your PC? Yes, the heterogeneous one is the typical one that you have in the first system, and since the core that probably you have in your smartphone, let's say, well, maybe not a smartphone, in your PC, is coming from the very old 8086, is using this heterogeneous architecture. But if you check an embedded system, which is, for example, using an ARM core, you will see that in that case, we have a homogeneous architecture. Okay? Now, if you check your PC, could you be a bit more precise? Which kind of architecture do you think that it has? How would you call it? Perfect. Some students said a CISC. There is some CISC, there is some RISC, there are some differences. Is there something else about besides this CISC and RISC? Let's say you are developing one processor that you want to put in a small TV set or in a printer. Which kind of architecture are you going to use? RISC will be an option. Is there something simpler? And actually the point, yes. So if we are precise, you could separate three kinds of computer architectures: stack machines, accumulator machine, and register file machines. The idea of the stack machines is that we have something like a stack. Here you have it. A stack is just a collection of positions where you can access the last ones. Yeah. And then your instructions are just taking the two last elements of your stack and then working with them, saving the result. Yeah. In this architecture, you don't have to say from where are you taking the results. They are always coming from the stack. This architecture is the simplest architecture that you can imagine. It is used, for example, in some booting architectures, but also it's very important because it is used in, for example, the Java virtual machine. Yeah, this is the fundamental architecture, the simplest architecture that you can imagine. If you just try to buy a small microcontroller, you will see the architecture that it has is what we call an accumulator machine. The idea is that we have our arithmetic logic unit doing some operations, but all these operations are always saved in one special register that we call the accumulator, which actually is also the source for the result. Yeah, you can take the other source from the memory, yeah, but one of the register is always the accumulator. This special kind of architecture is also very, very simple, and it is used in cases where you don't need very high performance and you want to have something very small, as said, like the microcontrollers. And then the third step is the so-called register file machines. The idea here is that we have some registers, yeah, not just the memory, some registers inside our core, and then we operate with these registers. We can move data from the memory to the register files, and then we operate with the registers. This is the performance processors. And inside this kind of architecture, then you can see that there are two alternatives, CISC and RISC. Okay? Again, I believe, red point, this is one of these fundamental slides that you have to know very well. I see that there are some students having some problems with the audio. Clear, these three architectures? As an example, here you have the kind of instructions that you can have. If you are working with a stack machine, you will have instructions like this, push, store, add. Here you have a typical instruction, add, with no arguments. You are adding the two elements in the stack, that's all. You don't have to specify anything. If we are working with an accumulator machine, this is the typical instruction that we have, add M. You specify me one position of memory for one source, but the destination and the other register is the accumulator. Of course, you also have some instructions just to work with the accumulators, yeah, but here is the fundamental one. And then if we are working with a register file, then we have instruction like this. We are doing the operations, but we are using the registers for doing that. We can have 2 registers, 3 registers, it depends. Of course, we also need some instructions to load and to store the registers, but you see fundamentally, all the normal instructions are working with registers. Clear the idea? Good. Yeah. Now, summary of something that you have seen twice, 3 times, 4 times, 8 times already. At the very beginning, people were thinking, okay, I want to create one architecture. My problem is that I want to write in a very high level language like C or Python or whatever. And because of that, there is a gap, yeah, between the architecture and the language. So maybe the best architectures are going to be those which have instructions which are very, very, very complex and very, very powerful, so that we can remove this semantic gap, so that the instructions are close to what I have in C. With this idea, the first processors were created, like the Intel 86, VAX, and so on and so forth. Yeah, they have very integrated instruction sets. The size of the instructions is not homogeneous. The advantage is that if you do that, the program is very compact. At some point, people start to analyze this kind of architecture with more detail, and they realize that yes, the code is very small, but actually it's very easy to make a mistake, and they are very hard to implement in hardware. And because of that, the hardware is not running very fast. With this insight in mind, people develop the so-called RISC architectures, reduced instruction set architectures. The idea is to have a hardware which is as clean and as simple as possible. Why? Because if it is very simple, then we can implement it very easily in hardware, and the hardware is going to be very fast. And then how are we going to address the semantic gap? Well, you will take your code, and then you will need a very, very powerful compiler to do this, let's say, semantic gap. So the characteristic is that we have few and very regular instructions. All the operands are using the registers, not the memory. Yeah. Because of that, things are working very, very fast. But the disadvantages is that we have larger programs. We need more instructions to do exactly the same. Yeah. But they are running faster. Examples are RISC, MIPS, ARM, and so on and so forth. Almost all the new architectures are based on this paradigm. Clear? And if you want to take one example, in embedded system, our processors, they are RISC. In your PC, you have something coming from the old days of the x86, and because of that, they are CISC. Good. Here you get a couple of typical examples of the code that you can write for a CISC and for a RISC. Using RISC, normally you are using registers, but you have very complex instruction, maybe reading from memory. Here you have it. While in the RISC architecture, you have to load everything in registers before you can do the instruction. Good. As an example, here you have the typical architecture, the typical instruction that you have in the MIPS. I believe, again, this is an important slide. We are going to use assembler code from time to time, and you have to remember this kind of addition, this kind of instructions. For example, here we have one addition. It's just in assembler code add, and the mean is that the destination is the sum of the source. This is the destination. These are the two sources. You can also do a logical AND. Then here you put an. You can do a jump, but not any jump. Jump only when equal. So if register RS and RT are the same, then you are jumping to one position in memory. If no, you just continue with the next. We have another instruction, which is just jump. You always jump without checking anything. We can load one word from memory. Tell me the register, tell me the location of memory. You can do different logical operations, NOR, or whatever. Yeah, you can store words. You can subtract. You will see that almost all the instructions, these, are basically the same. Yeah, they are just doing some operations. We have also some branch instructions here or here. And then we have instructions for working with the memory, like load or store. Yeah. Yes, there is one instruction. What means im? It means an immediate value. Yeah. Just to make sure, is any one of you, has someone of you never seen a piece of assembler code? Yeah. Let me try to refresh the key ideas of this assembler code. So fundamentally, what we have is sequential instructions, what to do. Yeah. So here you have the name of the instruction, what is what you write. And actually this is the meaning. Yeah. So if you write, for example, this instruction at RDSRT, then what the processor has to do is in the next clock cycle, he has to add these two numbers and to save the result in the other register. Yeah. If you have one AND instruction like this one, the processor has to read the source and then to write the result. Yeah. So the difference, let's say, between C and assembler in a very simplified way is that the only things that we can execute are very, very small steps. If we have a risk, we can just do one operation, sum, subtract, logical AND, logical OR, something very, very simple. We can just load from memory one value and to put it into one register, or we can save the value that we have into one register into the memory. Yeah. If you have a processor, then you have a program counter that tells you which is the next instruction that you want to execute. And the point is that you can change this programming content, and this is a jump. Maybe you have one instruction which tells the processor, I want to jump to this new position. Always, I want to do that. This is a standard jump. But it is also possible to say, no, I want to jump only under some conditions. And in particular, in the MIPS, the condition that you can put is whether two registers are equal. Okay. Yeah, I think probably the only thing that we need in terms of assembler is just to be able to read somehow some pieces of code. In most of the architectures, these registers is the local information that you want to hold, and there you can put data or you can put address. Yeah. The only important point is the PC, which is just saving the location of the instructions. Okay. Let me go again to this fundamental slide. Here, you see that a computer, it has one special register, the program counter, that tells you where do you want to read from memory. Here, you read one instruction, this instruction goes to the computer, and then the computer is doing something, doing one addition, one whatever. If we have a register file, second fundamental slide, here we have one value in one register, here we have another value, we can read them, and then the result is written again into the registers. Yeah, probably these registers are coming from memory, but all the logic operations that you have, addition, multiplication, and so on, they are coming from this arithmetic logic unit. Okay. Just for some of you, where you have a background about processor, which is maybe smaller, just let you know that I have copied all the relevant slides in StudIP from Digital Technologies, so that you can have not just this very short summary, but also you can have a refresh about digital technology in general, and a bit more in detail how the processor works. Good. Okay. Next point. If we want to have one processor and we want to make this processor to run as fast as possible, the best idea, or one of the first ideas, is to add a pipeline. The idea of the pipeline is somehow easy and hard at the same time. Imagine that you have one instruction that has two parts, A and B. And you want to do that into one clock cycle. If this guy is taking 1 nanosecond and the other part is also taking 1 nanosecond, then somehow for executing these instructions with part A and part B, you will require 2 nanoseconds. Yeah. The idea of pipelining is here to introduce one additional register. The idea of pipelining is to cut your instruction into small parts, yeah, in such a way that now for the first step, you have 1 nanosecond. And for the second step, it can also be done in 1 nanosecond. If you are working in parallel with block A and block B, then your clock can be 1 nanosecond, and then you have done the same thing that here you will require 2 nanoseconds. Okay? So if you want to see that graphically, here you see that we have instructions that in one clock they do part A and part B, and instead of that, what we have here, yeah, zack and zack, you see we have cut this in parts so that in one clock cycle we do this part A, and in the next clock cycle we do the part B. Yeah. The point is that since we are working in parallel, while here we are doing the part B, we can already do the part A of the next instructions. So we have two things, A and B, working in parallel, and because of that, we can try to go faster. Good. This idea of pipelining is very, very commonly used almost in any architecture, DSPs, processors, accelerators, and so on and so forth. Okay. One fundamental point of pipelining is that normally this can only be done if your architecture is moving the data only in one direction. If this is the case, you just cut here, put here some registers, and everything is working fine. Okay, good. Very important idea, that of pipelining. Yeah, somehow pipelining is equal to parallelization. If we go to a processor, maybe can you try to tell me some of the steps that you have to do to execute one instruction? What would you say? Yes. You see, there is a lot of small steps. First, you have to take the instruction from the memory. You have to read from the memory. Then you have to see what the hell is this? What is the instruction that you have there? What do you want to do it with that? You have to read the register. You have to execute, do the addition, the multiplication, whatever you need. Yeah. Maybe you have to read from the memory. There's something else, another step that you have to do. Yeah. You also have to save the result. So all these steps have to be executed. If you try to execute all these small steps in just one clock cycle, your clock is going to be very, very slow. So our idea is to cut the instruction in these small steps so that in one clock cycle, you are executing just one of these steps. Okay. Now, if we cut the instruction in pieces, can we do that easily, or can we have some problems? So it's hard. We can have some problems. Why that? So here you mentioned the word hazard. Why is this? Why can't we have problems? as you already discussed in the exercises, the key point is that when we have some program, yeah, we may have some dependencies, we may have some hazards. And actually, when you see the schematic of a processor, you will see that these problems are coming when you have information flowing in the opposite direction. Yeah. So if we analyze these hazards with a bit more detail, you will see that you can have hazards because of a resource conflict. Yeah. Maybe we have two steps in one instructions that would like to read from the same position of memory. We have a problem. Data conflicts. Maybe we have a problem if one instruction requires to read some results which have not been yet written by the previous instruction because we have cut it in pieces. Yeah. Or control conflicts. Maybe we have one jump instruction, but whether or not to do the jump depends on the result of some instructions, which is not yet done because we have not done all the super steps. So all these can produce a problem. Yeah. In particular, if you are working with an easy risk architecture, the two most important problems are data conflicts and control conflicts. Yeah. For me, somehow, it's easier to see this in terms of hardware. You can try to think that in terms of software. For me, it's somehow easier to see it in terms of hardware. Here we have it. So let's try first to discuss which are the typical steps that we have for executing one instruction. Yeah. We have the memory. Here it is. So here is our memory. We take our PC, we send the PC to the memory, and then here we have our instruction. So first part, we have to fetch the instruction. Now when we have the instruction, we have to decode this instruction. We have to know what do we want to do with this instruction. And at the same time, we can use the information from the instruction to read from the register file. And from here, we take the values that we need for executing our instructions. So in the second part, instruction decode, we are doing the decoding, but also reading the operands. Yeah. Now we have the operands and we know that we want to do an addition. So here we can do the operation. Yeah. Now we have the result. This result has to be saved. Maybe we have to save the result into the memory. We can do it here. If no, we just send the value to the next block, and in this block, we'll save the result of our addition. Okay, you see, we have 1, 2, 3, 4, 5 typical steps. Maybe our instruction is to read from the memory, no problem. In this step, we will read and we will set here the result. Yeah. If you have followed me, almost all the time, it seems they're working just in one direction. The information is moving from this part to that part. Perfect for the pipelining. But actually not always. Once here we have the result, this result has to be written back into the register. We have to write the result into the register. And because of that, here we go in the backward direction. We have a problem if we have two instructions. One instruction is updating one register, and the next instruction wants to read from that register, because it will take a while, 1-2 clock cycles, until this register is actually written. Yeah. So here is where we have our first problem. And what is the second problem? Here with the PC. Normally the PC is incremented by 1, but we have some instructions that are updating the PC only after comparing two results. if you compare two results, you change the PC, then you see that here, the information is also flowing in the opposite direction. And because of that, we may have a problem. So if you have a giant, there you can have a problem. I believe, again, these two slides are some of the fundamental slides of one processor. Good. For those, we have a smaller background in processor architecture. Are all the steps 100% clear? Good. Second fundamental point. Clear why do we have fundamentally two big problems, one's related with the data and the other related with the PC. Good. Here, maybe you can see it a bit more graphically, these problems with the hazards. So we have two instructions. What I want to do in this first instruction is just to add these two registers, the register 0 and the register 1, and to save the result in S0. And then I have another instruction where I want to subtract S0 and T3 and to save the result in T2. Let's see what happened. In the first clock cycle, I know I want to do a clock cycle, I read T0 and T1. Then in the third clock cycle, I do the addition. In the next clock cycle, I could do something with the memory. Here, I don't need it. And only here, I write my result, the sum, into the memory. Now let's see what happened with the second subtraction. If you start here with the instruction fetch, then you will realize that you have a problem. We have to start later in such a way that here we read the instruction, here we read the registers, and why here? Because only at that point, only here, we have update S0 with the result. So if we delay this instruction by 2 clock cycles, inserting 2 bubbles, then everything is fine. But if we don't do that, then we will have a problem. Obviously, the performance of our processor will be very slow if we have to insert these bubbles from time to time. How can we try to avoid these bubbles? The idea is the so-called forwarding or bypassing. The idea is that when the first instruction has the result in the ALU, we will take directly this information for the second instruction. We do not wait until the instruction, the register has been written. We take it directly from the memory. Sorry, we take it directly from the ALU. We have to see how do we do that, but in principle, after this clock cycle, the arithmetic logic unit has already done the addition. So why not to take the value from here for our second instruction? If we do that, everything will be fine. Yeah? Let me go back 1 second to our old slide. Here, and what you see is that when you do some operation from the ALU, normally you are taking the result from here. Yeah? But in some cases, you are taking the result directly from here. In some cases, you are taking the result directly from here. This is the forwarding. To take the results that we need, yeah, before the registers have been updated. In that sense, the subtraction, the execution of the subtraction happens before we have written the register. Yeah. So if we are using this, if we have this, let's say, architecture, you will see that first we read the first instruction. I want to do an addition. Then in this clock cycle, we read the registers T0 and T1. And at the same time, we read the second instruction. I want to do a subtraction. In the third clock cycle, here, we do the execution, yeah, and we read T3, but not S0. In the third clock cycle, the first instruction is not doing anything, but the second instruction is taking from the memory T0. And then now you have T0, from here you have T3, and then you can do your subtraction. In the next clock cycle, the first instruction will update. This guy will not do anything, and then in this clock cycle, the register T2 will be updated with the subtraction. Okay, you see this idea, yeah, is making your hardware faster. Yeah, you see the subtraction. Here we have one question in the slide. The subtraction requires T0, and we are taking this value as soon as we have it. We are not waiting until the value is saved into the register. We are taking S0 as soon as we have it, because the subtraction register, the subtraction instruction requires. Just that. The subtraction needs S0. Let's take it as soon as possible. Good. Remember, to do that, you have to implement some multiplexers. You have to do something in hardware. If not, it will not work. Good. And second fundamental idea. Now we have one instruction which is storing in S0, yeah, the value that you have in the memory 20 plus R1. And then here we want to do the subtraction again, reading from S0. What is the problem now? When you check ready, this instruction is producing the result from the memory here. Here you have the result. Once you have read from the memory, you can take that value into the ALU, but not before. This means that this instruction has to stop to wait one clock cycle, because the result is not coming from here. The result has to come after the memory operation. So if you have a load operation and the destination register equals to the source of the next instruction, then you have a problem. Okay? And this problem can be reduced to one clock cycle instead of two, adding a bypassing. This is a bypass from the memory itself. Good. But this guy cannot be avoided. Because of that, if you have a RISC processor, you will see that the compilers are moving the instructions in an intelligent way, in such a way that you never have instructions like here, where the destination of one load operand is just one clock before an arithmetic operation where you have to read from that register. Yeah, compilers are so clever that they try to separate that if it is possible. And with this, your penalty will be smaller. Okay. Good. In the same way, you could see that we can have a control problem if we have a jump. Yeah, here we have one example. Imagine that here I'm adding the register 4 with the contents of register 5 and register 6. Here I want to jump, but only when S1 equals to S2. Only if they are equal, I will jump to the position 40. And here I have another instruction. Yeah. When do we know if we want to jump or not? We only know it here, after the ALU has done the comparison. And because of that, the PC for this instruction, whether to take a jump or not, has to be delayed by 1 clock cycle. Yeah. Again, for the jump, we have a problem. In the particular architecture that we have, this penalty is only 1 clock cycle. But if you have a modern microprocessor where the number of steps that we have is very high, you will see that the penalty for a branch, especially for a branch that we have taken in the wrong way, is very, very high. And because of that, almost all the new architectures, the complex one, they have some block where they try to predict the jumps in such a way that even if they are not sure, the probability of taking the right branch is very high, and then this penalty that we have seen before is not commonly. Yeah. Clear? I believe, especially, we can control as art, you have to know it, but I believe especially these 2 slides, how forwarding works, they are again fundamental. Fundamental to understand it from the logical point of view, and fundamental to see how this is done with the help of these wires. Good. Questions about this fast review of the processor? I said, if there is any question, maybe you can contact me, you can contact Ardalan. Yeah. Yes. Something coming from one question. Maybe you can do it in the slide. I see that there is some question from one student. So if you are looking for a book, I said the Hennessy Petersons are the best, are the easiest. Yeah. You can see in the bibliography we were recommending before. You can see in the next slide the Patterson and Hennessy books, which are in the library. Are already as ebooks, so you can take them. And you have a very easy description of the results, sorry, of the lecture. Okay. Some more questions? Sure. Then everything fine for the moment. I said, I presume for some of you it was pretty easy, just a review. Maybe for some of you it was a bit more complicated. Yeah. Clear? Then thank you very much for your attention. Remember that today we don't have exercises. We will have them in 2 weeks. And then for some of you doing VHDL, that's see you in a couple of hours. Enjoy, keep safe, see you next week. Ciao.